Good day and welcome to this lecture. In this lecture, we will be dealing with erosion modeling in Aspen Hysys. Now, erosion modeling involves the modeling of erosion using the Aspen Hysys software. Basically, in flow assurance, we have erosion as the material degradation of pipeline walls, equipment, or components caused by the high velocity flow of fluids containing solid particles such as sand, scale, or debris, right? So basically, it's just the wear of material due to high velocity flow. That's basically what it is. Now, the cause of erosion is basically the solid particles in the fluid stream, right? So you have solid particles contained in the fluid that is flowing through either the pipe or the equipment, right? So these solid particles are the causes of erosion. Now, when the fluid flows in very high velocity, these solid particles lead to the wear of the material used that was used to actually construct either those pipes or equipment, right? Now, the effect, so basically over time, the material is weared off, right? And it leads to the thinning of pipes. It can lead to equipment failure. It can lead to leaks. Then it can also pose environmental risks, right? So basically, for this erosion modeling, we have a couple of parameters that actually affect erosion modeling, right? So some of the parameters include you have solid concentration, which has to do with the amount of solids that is present in the fluid. So an increase in solid um, concentration will lead to the likelihood of more erosion happening as the fluid is flowing, right? Then you have particle size and hardness. If the particle size is larger, there is a more likelihood for erosion to occur. Then you have flow velocity, right? So erosion increases with velocity, right? With increase in velocity, right? Increases with increase in velocity. Then you also have fluid density that is also proportional to erosion, the amount of erosion that can occur, right? Then you also have fluid viscosity. For fluid viscosity, it depends on the flow regime. Then you also have also the flow regime can actually determine whether erosion would actually occur or not. So some of the flow regimes that can actually cause erosion are turbulent flow, then also slug flow as well, right? So if you have turbulent flow, there is a likelihood that erosion might occur, right? Can occur. Then you also have pressure and temperature, right? So pressure and temperature also have or play a part in how erosion would actually take place in pipes or equipment, right? Now, a very important thing to note about erosion is that erosion will occur if fluid velocity is greater than erosional velocity, right? So this is a very important thing to note for erosion modeling in software, right? So you have to know that if the fluid velocity is greater than erosional velocity, then erosion would occur, right? Now, moving forward, in multi-phase flow through pipelines, we have the continuous impact of particles on the wall surface can lead to erosion along the pipe, right? When sizing and designing pipelines, these effects are monitored by ensuring the velocity in the pipeline does not exceed a maximum value, right? So the velocity in the pipeline should not exceed V max, which is given by C times um, density raised to power minus 0.5, right? Now, the mixture density, PM, is based on the following volume fractions, right? So the formula is displayed on the screen. You have QL over QL plus QG times rho L plus QG over QL plus QG times rho G, right? This is used to determine the mixture density that is subsequently used to determine the maximum velocity, right? Okay, so um, we have Q as the volumetric flow rate, right? And then uh, L and G would refer to liquid and gas phases respectively. So QL is liquid flow rate, while QG is gas flow rate, right? PL is um, liquid density, rho L liquid density, and rho G is gas density, right? So rho M is your mixture density, that's the density of both the liquid and the gaseous phases respectively. So for modeling of erosion, right? The modeling of erosion, we have different correlations that can actually be used to model erosion, and some of them are actually highlighted in this table. So I would ask you to actually pause the video and actually take a proper look at each of these correlations. Um, some of them include the API recommended practice 14E, right? And you also have the formula on the screen. Then you have the Salama and Venkatesh, right? You also have the DNVGLRP0501. You have Jenkins et al. So you can actually do well to actually pause the videos to look at this table properly and also know when they are used. So we also have a column that guides you on when to actually use which of these correlations. Then below are the explanation of each of the variables that are actually in the so-called correlations that have been listed above. So you have these variables for correlations. So you can pause the video to actually take a look at this properly at this section, so you have good understanding of when to use these correlations. Then moving on, we have yeah. So next we have the popular or the correlations that are available in Aspen Hysys, right? We have the correlations that are available in Aspen Hysys. So these are some of them, right? For Aspen Hysys, you have the API recommended practice 14E for continuous service and non-continuous service. Then you have the Salama and Venkatesh of 1983. And then you have a user-defined option where you get to actually specify your own correlation, right? And each of them have values of C, right? They all have C values. They all have C values that would actually be used to determine Vmax, right? Vmax that we highlighted earlier on in the video, right? So you have C, each of them have different C values, right? That is used to determine Vmax, right? So we also have a table here. Yeah, we also have another table here that actually helps you have an idea on which correlation to use and why you should actually use them, right? At this point, we will just go over to the software to actually see how modeling erosion in the software actually works, right? So for that, we'll be making use of a section of this particular model to actually do this illustration. So we start with the components. Let me see if I can copy this. Okay, let me see if I can copy. Okay, so I will just do this, but I have to start. Okay, I have to add the first, so I would copy the remaining and see if it works. Let's see if it works. So the first component there is nitrogen. That should be N2. Okay, then let me see if I can paste the rest. No, it's not working. Okay, so we have to specify each of the components individually. So we have H2S and CO2. Okay, that should be easy. Then we now have hydrocarbons that follow. So we have from methane to N-hexane, from methane to N-hexane. Okay, so I have mistakenly put in N-hexane. I want to just copy all of them at once. Yes. So I'm adding all of them together. Okay. Then next we have H2O and ethylene glycol. So we can add those H2O and ethylene glycol. Okay, we have that here. Okay, so the component list is complete, right? Component list is complete. Then for the fluid package, let's see the fluid package. Okay, we are using pengrub, so just use pengrub for this. All right, so we are in the simulation environment. We just make use of the data that we have in this particular model. So we are using the feed information here. Okay. Okay. So we have 8.5 degrees Celsius, pressure of 1548. So we can bring out a pipe from the piping and hydraulic section of the model palette. Then we can add inlet and outlet streams. Uh, okay. So we are just going to model one pipe since it's just an illustration. So from the worksheet, we can specify temperature as 8.5. Then pressure is 1548. I think it's mass flow rate that is 2E5. So we are going to confirm that 2 okay it's 2.5 E4. Pressure is 1548. All right, that's 2.5 e raised to power 4. Yes. And for composition, we can start with nitrogen, then copy the rest. Okay, so we have 0.068 nitrogen, 0.068 nitrogen. Then we can copy other values from this. So we can do this. This should actually copy. Okay, so it's not summing to 1. So we have to confirm what it's supposed to sum to 1. 0.068. Okay, 0.0068 actually. So that's the mistake. So it's supposed to be like this. So you have your total as 1 for composition. Okay, so by now the feed stream is fully specified. So we need to specify the pipe, the specifications of the pipe now, right? So we close this and we open this to check this pipe specs. We have already treated pipeline modeling. So if you missed that particular video, you can check simulations with Aspen Hysys. You will see where we illustrated how to model pipes, right? So this particular tutorial is for erosion, right? Strictly for erosion. So I'm just going ahead. Okay, so let's see what we have here. So for the segment, we just have one segment here. So we are going to make use of that. You have pipe length as 3000, elevation change is 0. Okay. So you add a segment. So we have length is 3000 and elevation change is 0. Then we need the inner and outer diameter. So we have 323. Yes, so we pick let me see. Okay, I think it should be schedule 40. Okay. Um let's see, 300. 323, yes. Outer diameter is 323. But let's confirm the schedule. Let's see the schedule. Okay, yes, so it's correct. It's schedule 40 and nominal diameter is 300. So nominal diameter is used to calculate, the software uses nominal diameter to calculate the inner diameter and the outer diameter. So nominal diameter is 300 millimeters. So it calculates the outer diameter as 323 and the inner diameter as 303, right? Yes, so we are good to go with this. Okay, so we continue. We have heat transfer. So heat transfer, we have the ambient temperature as room temperature, which is 25 degrees Celsius. So we specify that here under estimate HTC. So you have 25 degrees, 25 degrees. Then we have include this and then include outer HTC. So we have been able to specify the pipe, right? So this is just for the illustration of erosion. So let's go back. I want to confirm that this has the same data as this first pipe, apart from, so it's basically almost the same thing apart from the pressure and the mass flow. Yeah, so because I will be making use of it. So yes, the composition is the same, right? So let's go back to our model. Let's go back to our model. So this pipe we have simulated, I will just create a copy of it on the flow sheet. So I will copy it and then I will paste it here by the side, right? So basically these two pipes have the same specifications at this point, right? Both the streams and pipe specs, right? They are the same. So I will be making changes on this second pipe to actually show you the effect of erosion, right? So for this first one, to start up the erosion modeling, all you need to do is go to flow assurance. So you have the flow assurance tab at the top, right? So you just click on it. Previously, we worked on CO2 corrosion and hydrates, right? So today we are working on erosion. So click on erosion, you click on erosion, and then it brings out the erosion environment, right? Then here you can specify your um, correlation, right? So these were the correlations I displayed earlier in the video. So you can specify whichever suits your model, right? So when you are satisfied with selecting your correlation, you click on do erosion calculation, right? So you click on it, right? So when you click on it, you have your plot and then you have your table, right? You have your plot and your table. From your table and your plot, you can make inferences. Now, remember what I said earlier? I said, let's go back. Let's go back to, so we have that for erosion to occur, fluid velocity should be greater than erosional velocity, right? So to determine whether erosion will occur in this pipe, you have to look at the fluid velocity plot and then the erosional velocity plot. Now, erosional velocity plot is the plot in red, while the fluid velocity plot is the plot in blue, right? So from this particular graph that we have here, erosional velocity is greater than fluid velocity. And based on this, right, based on this, erosion will not occur in this pipe, right, because erosional velocity is greater than fluid velocity, right? Normally, for erosion to occur, fluid velocity is supposed to be greater than erosional velocity, right? So now we will now use the second pipe to illustrate erosion, right? So I will change some of the parameters in this feed stream. So I will change it to what we have in the other model, right? The second pipe. So I will change it to the values we have in this. Now I'm going to increase, yes, I'm increasing my pressure to about 2000 kPa, right? And then I'm reducing the mass flow, I'm reducing the mass flow to, okay, I'm increasing the mass flow actually. So increasing the mass flow to 1.5 times 10 raised to power 5 kg per hour, right? So we are going to be doing that on this our illustration. So we are increasing this to 2000, this 2000 kPa, right? And then we are increasing this to 1.5 E5 kg per hour. So after specifying the pressure and the mass flow rate, we have this message here that says solid particles have been detected inside the pipe. So what I want to do is I will also adjust some of the pipe specs as well. Now this is just to illustrate how the erosion would occur in the pipe, right? So most of the values are just based on assumptions. So from here, the model we are using, the pipe length is reduced to 100, then the nominal diameter is 250. So we're making those changes in our own simulation. So I'll just reduce this to 100 and then reduce the nominal diameter to 250, right? Then let's see if we can also do that for this initial pipe. So going there, we reduce the nominal diameter to 250 and then um, let's just use a pipe length of 100. So let's see if there will be any differences between the plots for each case. So we go to flow assurance and then we go to erosion. So erosion, you have erosional velocity is still far above fluid velocity, and that means erosion will not occur, right? So but we come over here and we go to hydrates, we go to erosion rather, right? So normally you are supposed to click on do erosion calculation, right? So you click on it and then it generates your table and your plot, right? So if I click on the plot, you see that the fluid velocity is above um, the erosion velocity, right? So if there's a way I can try to have both charts on my screen. So you have the fluid velocity above the erosional velocity. So in the case of this second pipe, erosion would occur, right? Because fluid velocity is above erosional velocity, right? And from the table, we have fluid velocity, which is the bulk velocity, is above the erosional velocity values, right? The bulk velocity values are above erosional velocity values. And based on this, we can infer that for this second pipe, erosion will occur, right? And you will notice that it was after increased I increased the pressure and the flow rate, right? The pressure and the flow rate. I believe that flow rate has an influence on velocity, right? So an increase in flow rate should lead to an increase in velocity, right? So basically, I want to believe that that is what affected um, this particular pipe, and that is why erosion will actually occur, and you have the bulk velocity higher than the erosion velocity, right? So we have been able to see how some of these parameters can actually affect um, the pipe model, right, as regards erosion formation. Now, one important thing I want to also point out is that the composition of the fluid flowing through the pipe, right, or the equipment can also have an effect on erosion, right? So hydrocarbon compositions with higher erosion risk would include gas-dominated streams, right? Gas-dominated streams. Then you also have condensate-rich fluids, right? So you have condensate-rich fluids. Then you also have multi-phase mixtures that consist of sand particles, right? Then you also have sour hydrocarbons, right? So basically, sour hydrocarbons would actually lead to uh, erosion that is also accompanied with corrosion, right? Right. So sour hydrocarbons, right? So these are some of the composition of fluids that can actually lead to erosion, right, in pipes, right? So basically, we have come to the end of this particular tutorial. If you have questions, kindly let me know in the comment section, questions or observations. Then also share this video with your friends, and then subscribe to this channel if you have not done so yet, so you can get notifications about subsequent videos. Thank you for joining me in this particular tutorial. Do have a good day.